one is not touch screen? Okay, so you will not be able to write on. I don't know if you were planning to. So, well, thanks much for making your election for electing to come here. Today we have a second group meeting per week, and Aaron wanted so much to present an update on his research. So, floor is yours when you are ready.
And we of course don't have any meetings next Friday because it's a holiday.
Holiday.
Yes, Good Friday.
Oh, Good Friday.
Yeah.
And then Monday is holiday as well.
Never do that on a holiday.
Wait, Friday and Monday?
Yeah. Yeah, so for classes the schedule is
And I plan to distribute printed copies of.
we should say comments like everything is wrong.
Well, you wouldn't be wrong with that.
So, if there are not enough color copies, there are black and white copies. Enough color for everyone? And let me focus it on you and on the screen. No? No.
If we don't have anyone on the website, then it's, connected to us, and it doesn't matter.
Or maybe.
Oh, you are still recording it.
Yes,
right?
we are recording. Okay. Later make a movie. Excellent research of North Dakota. Okay. Now you are under the focus.
Okay, so I think last week Dimitri emailed me asking if I'd present something about my results this Friday, and I figured, why not? Plus, he probably didn't trust me to sit down over the weekend and actually write out my results, or try to strategically plan how I was going to write my results. And he's right, I wouldn't trust me either to do that. So it's a good prep work to what I'm actually going to write for the paper. So here's what I plan to talk about for most of the presentation, and I'll kind of pick this image apart as we go along, and hopefully by the end it will look less like abstract art and make some sense.
This is beautiful outline.
So the first thing we're going to look at is ground state electronic structure for the two systems I'm looking at, or the two quantum dots I'm looking at. On the left you can see the intrinsic quantum dot, which is passivated with ligands, and on the right is basically the same quantum dot, except one of the LEDs is replaced with Mn2 dopant. And yeah, and it's important to get the ground state electronic.
Before you go, so what exactly you're doping here? Like marganes? You have doping only through the marganes atoms.
Yes.
And they are substituting lead?
Yes, just one.
Oh, just one.
Just the central one that's boxed out in the
Then
image.
why is it X, 1 minus X?
Um,
If it's just one, then the formula is clear, right?
right, I guess I was just using general notation
Okay.
for stoichiometry. Because, well, if you did stoichiometry, it would be
But
like,
what is it? Switch the positions or
It should be lead.
PB 1 minus X?
The X for small concentration, X close to 0.
yes.
So it should be manganese X.
Oh, yeah,
lead,
you're right.
lead.
PB, yeah,
Right.
Yeah.
PB is 1 minus
Should be
Backward.
PB 26
minus
over
one.
27, and then 1 over 27, whatever those percentages
You have
are.
27 LEDs?
Yes.
It's actually 26.
Oh,
Yours
and-
are just not.
And you may mention literal number of atoms composition. There is nothing shameful to tell about it.
What do you say, guys?
It should be.
With that prompt, there's
Ask
100.
the author. How many cesium?
How many cesium? 8?
I think 8.
Yeah. There's one at the center of each cube, because it's a 2 by 2 by 2 unit cell. So there's 8 cesium.
Yeah, the actuals, because you're not varying the size of the quantum dot, right?
Right, they're both the same size. They're both.
Yeah, so then you probably really need to present the
Composition?
actual, like, how many atoms you have in your quantum dot.
Okay.
So cesium 8, lead 27, manganese, bromium 3 only.
Alright, that's the stoichiometry. So there would be 54.
Yeah, I guess that this like actual size of the quantum dot.
Right.
Right, because it's not like in a lattice where you just have a unit cell and then it just replicated.
Mhm.
Or you can put like a unit cell, but then tell how much it was replicated. 3 times? 2 times?
Two.
Two.
2 by 2 by 2.
Yeah, which is awkward, right? So I guess you probably just give the exact number of
Okay.
atoms you have in the cell.
Okay.
Because it also gives you a good idea of overall how big the system is,
Mm-hmm.
the actual size of your system.
Okay, so then, I'm sure someone wrote that down, so I'll remember to include that one day. So,
And before you go, so when you show in this octahedral configuration for your manganese, manganese 2 plus in a bromium ligand field, right? So first of all, it's completely unclear where is the bromine, where is the ligand. So you probably can use a color scheme, and it's more like for your figures, for your paper as well,
Mhm.
right? You probably, maybe in your figures you had this information. Let's say, first of all, I don't understand, there are 2 different pink colors. Are they just, like in this picture, are they just for fun? Or they, well, you have light pink and you have bright pink.
here's one pink.
I do have.
On this manganese octahedral structure, this one, yeah.
Oh, it's a lighter, because it's.
Okay,
yeah.
so this
So
is
it's-
pink, not really the change in atom. So
Yeah,
this
That's
all,
just the software.
okay,
But
this all pink are bromine
Can
or
you
not?
come closer? I want to show something, and you to read one word in English. Depth.
Depth Q?
Yes. Do you know this word?
I know the words separately, but not together.
What does it mean?
Depth is.
No, second word.
Oh, queuing?
Yes.
Well, and
So if
it's
you,
showing the how
It's-
say,
it-
3D view or something like that,
it,
right?
it makes whatever upfront darker, whatever in dusk, whatever
Mhm.
is on the background, and in the representations in VMD you can click disable depth queuing, and then it will be the same color.
But each of these pink are bromines, right?
Yes, they're all the same,
Okay.
same atom.
And my understanding, I don't know is it really a point or not, but it looks like it has to be octahedral environment, right?
Yeah, that's what it's placed into.
But looks like, again, maybe just the way how you're showing, maybe it's because of the 3D view or something, but it looks like it's not really giving you the nice, ideal octahedral structure. You have like these angles being not really 90 degrees, am I right?
Right.
So it is true. And this is the purpose why you're showing this figure, to show that your octahedral is really perturbed octahedral. It's not 100% has a pure octahedral structure.
Right, because
Okay.
you can kind of even see. Like,
Well, I kind of
this-
see,
this
but I
is
was
the
not
shape.
sure, is it because of the view, right? Because, what, Dmitry, how you call it?
Depth
some,
queuing.
well, anyway, so the 3D kind of perspective vision, right?
Mhm.
When you have what is in front is brighter and larger, and what is going outside is kind of going smaller. And then it's really hard to see whether it's really 90 degrees angles or something else.
Mhm.
But in your case, and for your results, when you explain in your system, you probably will point out that it's like octahedral, but it's really perturbed octahedral.
Right, it takes. Well, it looks octahedral, but it looks.
But
I don't know,
perturbed,
explain it.
perturbed octahedral due to the manganese. If it's lead inside, then it's
Yeah, all the bond distances
Real.
are relatively the
they're
same.
all the same. But when you substitute in by manganese, then you have this
Some contract, some elongate.
some
and it's
perturbation. Okay.
a different environment. So that's what I planned on talking about next. So I just put up bullet points of what I planned to mention in my paper. I didn't put any figures because it would take a long time to go through them all. And I have it laid out as a 2x2 because for 2 quantum dots, we do 2 different sets of calculations for each one. So if we're doing geometry optimization, we do spin restricted calculations for the intrinsic quantum dot, and we do spin polarized for the doped quantum dot because we're dealing with transition metals, which can have a variety of different spin configurations. So you have to do spin polarized to get the correct electron configuration. And then once we optimize both of them, we do non-collinear plus spin orbit coupling single point calculations to include spin orbit coupling effects, because both lead and manganese have, well, lead has a large spin orbit coupling associated with it. Manganese has a smaller one, but it's still there. So to do accurate modeling of the photophysics, you have to include spin orbit coupling. So that's why we do single points for both of those. And the notable things to mention for both of these systems, just starting with the intrinsic spin restricted calculation, is it follows a typical electronic structure that's been reported in literature, where the valence band is made up primarily of bromide 4 or 5p, I can't remember. It's either 4 or 5p orbitals, but they're p orbitals, and then lead 6s orbitals, and then in the conduction band, the band edge is made up of 6p orbitals. When you can see that from when you do partial density states, or PDOS. So mention that follows what you'd expect for the system. And there's no trap states, which we'll get to eventually in a little bit. So you can trust it to be a reliable ground state optimization for the quantum dot.
So there is the absence of trap states is your achievement.
For that
Yes.
part, yes.
So there is a high probability of them to appear, but there are some tricks for the system that make
But
absence of
go in a previous slide. Like here, there is your trap states, right?
where
These are the dope, or I should have said,
Oh, this is doping.
these black lines are doping introduced.
But if you don't have doping, then the gap is open. You don't have any trap states.
Right.
And this is because you really have nice ideal passivation.
It's like a particle in a box. That's where you have the finite potential wells on the edge. So it roughly follows that idea. So electron density is inside the cube. So then for spin polarized calculations for the doped system, there's a lot going on there, because first you have to figure out whether it takes a high or low spin configuration, because those are kind of the two favorable for Mn2+ and a ligand field. And halides generally give they give high spin configuration, so 5 spin up electrons, which is what we found was the lowest total energy of the system. And that kind of follows what's been reported in literature when they look at these things experimentally. And then it's kind of complicated, because we looked at the orbitals, but the orbitals aren't very straightforward to analyze just by looking at them themselves, because you have crystal field splitting, which splits the d orbitals of the manganese ion. And then there also appears to be some distortion of the geometry, so it's not perfect octahedral. It's more like a square pyramidal structure, because if you look at this bond here, it's like 0.8 angstroms longer than all the other ones, and it's more bonded to a lead that's out here than it is to the manganese. So it seems like there's some sort of Jahn-Teller distortion.
So it's not just because usually it's a very common distortion when you have octahedral structure, right? And then the bond on an apical, or whatever you call it, on the top and bottom, from like you have 4 atoms lying on a surface, right? And then top and bottom ions, they are either longer than the bonds which are for your 4 guys which are in the surface, or shorter, right? So you either squeeze it or elongate it. And then it's also known there is some from the simple geometrical point of view, molecular orbital theory gives you the splitting between your d levels based on this perturbation. But in your case, your perturbation is really just kind of one bond is increased on a surface. I mean, those 4 which are laying on the surface.
It follows the trend you said. So within like a plane, they all kind of have the same bond distances. And then this one,
So my understanding is these 4, they are all on the same. These 4 which are this cross. I don't know.
this guy, that one, that one.
No. This is, I guess, top and bottom, right?
No, actually, he flipped that one in the
Okay.
here. So these cross 4 are in the same plane.
I saw.
The horizontal 2 is supposed to be
If
longer.
you come closer, you will see. I thought like these 4 stay on one plane, and these 2 are kind of outside the plane, right? Or not?
It'd be. I don't know, it makes more sense to me if you viewed this and this
Oh, I
like
see.
outside as the plane.
So,
So you may need additional labels if you want to show and discuss.
so this is your plane. This one.
Yes.
Okay. Yeah.
That's what I'm describing as the square.
And then all four atoms still are at the same bond distances, which are in the plane.
Yes, they're all roughly like 2.7 inch.
And those which are outside the plane,
This one's longer and I think this one's a little shorter.
huh?
Or it's a
So
little
that you
different than
have
the
top and
square.
bottom not symmetric. Wow. Okay, it's interesting. Because usually they go both shorter or both longer.
I think. I'm still trying to figure out exactly why it is. I have,
Well, check your symmetry, and you can also just Google. It's very easy to Google something like perturbed octahedral structure or something, and you will find some kind of splitting in levels, how it was, estimated just based on a simple geometry kind of point of view. If you have squeezed octahedral or elongated octahedral, how you have your dx dy orbitals are splitting, and maybe you will see very similar splitting for your predictions.
Yeah,
Yes, I did
that
do-
splitting is based on the ligand electronegativity. If you add the more electron donating ligands,
You already have
It's
this
very-
change
yeah.
in your lengths due to
Mm.
this electronegativity
Yeah.
effect here. But my point is that how this, because in a pure octahedral, you will have 3D and then 2D, right? But if you have this structure, when you have either, I don't remember exactly how it splits, but if you have either squeezed or elongated,
it
right.
goes like 2, 1, 1.
right, then you will have 2, 1, and 2.
That's
and
more
something
what I
like that.
see for the d orbitals. Or the
Okay, so you
ordinary
checked
d
it already.
I've started to. I can have to redo some of them, but
Okay. But I
yeah, I
think
do see
again,
the orbital ordering, and it's pretty consistent with what you'd expect. for
Okay,
the
but-
symmetry of the
But then maybe just again illustrative, maybe to put it in your figure, if you show in this kind of structure, right, you probably also can show your splitting in levels as it is expected from the symmetry. And then when you will be discussing your density of states and showing exactly how the splitting goes, you can refer to this expected kind of qualitatively expected picture in your d orbitals, and whether you see this or not with your spin orbit or without spin orbit interaction and so on.
Yeah, that would make sense. It's just I haven't processed all
I-
of it, and it's kind of I'm trying to find the best way to illustrate it too, because there's also the
Well, for
last
illustration,
way
it's
to-
really just how many 2, 1, 2, or whatever your splitting is, and maybe again, don't forget to cite the source where you're taking the splitting from.
right.
it's known as John Taylor distortion. So, by name, even so. it's just-
Taylor distortion can be applied to everything. It's not just for this specific.
For
Yeah,
okay.
I guess.
I
Probably.
mean, this is
Many kind of
yeah.
distortions has pretty much the same name.
Yeah, is,
Because the same guy was studying many distortions, not just
No, it
this
is
one.
two guys, John and Taylor. John
Oh,
Taylor.
oh, okay,
Yeah,
maybe
that's
John
one.
Taylor is something more special.
Maybe, I
But
don't know.
Taylor distortion is also distortion is very common for many other types of distortions. Yeah. But this is for elongation.
Just distortion of dihedral states.
I just noticed something interesting.
Oh, okay. So then, yeah, last point I was going to make is the. I don't know what that
No,
is.
you don't.
Anything.
It looks like a touch screen, but it is not.
So you get the level splitting just from the symmetry, but I also see hybridization of the d orbitals with the bromides, and even hybridization of these with themselves. So it's kind of have to sort through all of that mess too to nail down what's actually happening in the system. So.
Aaron,
Mhm.
do you plan to cover the following question later, or you are planning to skip it? The choice of charge and multiplicity,
Oh, is it charged?
oxidation and multiplicity. Is it like singlet, non-singlet? But do you plan to talk on it later, or you want to skip it today?
I was thinking maybe once I got to a couple more slides.
Okay,
bring it up. Well, at least
And your system, is it charged or it's neutral?
charged due to the ligands.
Oh, because your ligands are charged. I see.
Yes. Because the crystal structure itself isn't charged, because it's, unless there's some sort of vacancy or something. But yeah, the crystal structure itself is charge neutral. But with
Which
the
ligands again you use?
we'll get back to that point. That's going to be
Okay.
slides. So, okay, that was spin restricted, spin polarized. So then we do single points with spin orbit coupling, and what I plan to do is note typical about half EV reduction in the band gap due to the splitting of p orbitals from the lead, splits the spin states.
You
Which
use a spin coupling.
spin orbit
Spin
coupling.
orbit coupling.
And it reduced the band gap by about 0.5 eV, which has been reported by other people. And then I was going to do a PDOS analysis because of spin orbit coupling. You get kind of best way I can think is mixing of states, because that's what spin orbit does. It takes. I guess for this system, I'm not quite sure. It would make much
It
of a
takes your
difference.
S or P and
And it mixes
mix
them.
them.
Yeah, so they're
Yes.
more hybridized, so it's
So
more complex.
your S and P not anymore good quantum numbers. Means your L actually, right? Your
L and S, so it's J. Totally.
quantum numbers, yeah. L and J not really good quantum numbers in this case.
So be interesting just to compare the orbital analysis for HOMO and NUMO for both systems. And also compare spectra, because there could be changes in oscillator strings too if there's changes in the orbitals for all the states. And then for the dope system with non-collinear and spin orbit coupling, same thing, PDOS analysis, seeing how the orbitals change with the inclusion of spin orbit, and noting the spectra, and then we're able to see DD transitions, or spin flip transitions from the metal dopant, and then note the intensity of them, because it's there, but it's very, very small, very weak. So, next thing we add to our figure is we did our electronic structure. Now we're going to look at the role that ligands can play in introducing states within the band gap, or surface trap states, which is usually reported, which is one thing that's been called in the literature. And the expectation is that for the intrinsic dot, you can have ligands either oscillate with the bonds, and then you can see changes in oscillator strengths just due to bond vibrations, or they could even pop off during molecular dynamics. So if they pop off, or if there are any changes in oscillator strengths, you should be able to see that along your trajectory.
But do
Potentially.
they? In your results, when you run dynamics, your ligands are going out?
We don't see any pop off.
Ah.
We'll get to that in a second.
So
And then
hypothetically, it can pop up.
Mhm.
And generally, in arbitrary quantum dot or surface, you may expect that popping up of ligand will result in creation of trapping state.
Yes, which is bad because it reduces PL, and that's what these quantum dots are used for.
So you recognize possibility of this adverse effect and giving us heads up that this effect should be taken care of.
Yes,
Okay.
just setting the stage for results seen later. And the idea is that in the dope system, like even if dual ligands or surface states are created, like it shouldn't, the dopant doesn't care because it's protected on the inside. So its d orbital states are not going to be interfered with in these trap states. So the first thing to think about is if the ligands are going to pop off, it's like they'd have to have a pretty low binding energy. So a natural thing would be just to look at binding energies of the ligands to the perovskite quantum dot surface. And this top image up here just shows spaces on the quantum dot that I removed ligands from. So just looking at this top surface, altered it a little bit, you can see it took one of the acid groups off from the leads from the centralmost, because it's kind of it's least affected by other ligands, so you can get a better idea of just removing that ligand without any correlation effects from other ligands. And then I also just removed an amine that's adjacent to it, that's covering one of the faces.
Just a second, I'm lost.
It could be worse to show your inset, this plane, as a standalone image for the whole slide, maybe even from different aspects, and discuss it in more details. because
But-
spatial understanding is very hard.
But before you go, this is your first paper on this type of systems? You were not publishing anything before with the same ligands, with this quantum, with this perovskite dots?
We did thin film, and it was an amine, but it was.
Okay, but again, your story about the ligands. So first of all, you trying. I'm lost in a sense. Like, what exactly you expecting? You're trying to say that depending on a position, depending on a surface and position of these ligands, you expect them to interact differently with the surface, right?
Right. I just wanted to
And
look at
some
it
of them
nicely.
will be stronger and some will be weaker, right?
Yes.
And you are calculating binding energy of these ligands, or you popping it out and looking whether you create a trap states?
Eventually, yes. So here we're just looking at binding energies to see if,
So again,
like, if ligands can pop off.
right,
'Cause
you're
if
looking
it's-
on a binding energy for specific like tools, like you're not really going through each ligand, right?
Right.
How many of them you have. You take really the most representative ones
Right.
on that surface, and you have some reason why to look just on this or just to that.
Mhm.
And then compare the energy interaction with the surface, just calculating binding energy.
Yes.
Means you take it out, find the energy, optimize, after you take out the ligand.
Not the quantum dot yet. So this is
No, it's
just
not
like a
binding
rough.
energy.
Oh, I didn't relax surface of the dot. Is that what you mean by optimization?
Well, you got binding energy by definition. This is a difference in energy of the system with this attached group comparing to the energy of individual group and the system without that. But they all have to be in their relaxed form, in their minimum energy form, right?
So if
So if you're not optimizing the
it is
surface,
a rough approximation. Like if you do frozen binding energy, it is not quite binding energy. It is a rough approximation to the binding energy.
So I'm not saying these are the true binding energy. I'm saying these are rough estimates that are probably are overestimated to what the actual ones would be.
we don't know. It can be underestimated, it can be overestimated. Because when you take this ligand out, the energy might grow or might go down. We don't know.
True.
Because your binding energy telling you whether it's really energetically favorable to be with this attached group or not. Or not, right? Means when you not put in this group, maybe the energy would be low.
Mhm.
Aaron, so before you go into, maybe you were planning to jump quickly to the next slide, but before you focus on more details on this slide, on removing ligands, can you make a comment how the ligands were deposited? What is a pattern of setting the right ligands of different nature, anions and cations, and how do you decide where to put anion, where to put cation, and in which stoichiometry, how many
And
of
your
each?
anions not compensating for cations? Like you still will have a charge on the surface, on the quantum dot?
For this one, yes. Because we have 54 carboxylic acids and 48 amines. So it's not one for one.
Can you
So-
tell more
Yeah,
Yeah,
about
then it's
so
really
this
interesting
first-
why you doing this
So
in this proportion.
So we just looked at the oxidation states for both for lead and then the charge of bromine by itself.
Uh-huh.
So lead has a positive charge, so if you wanted to bind something to it, ideally
positive charges.
two positive charges. So you'd want something with at least two negative charges, or at least a negative charge. Or something that could donate electrons, density basically. And then for the bromines, they're negatively charged oxidation states, so you want something positive to bind to those. So we have our acids, these little red guys, they're coordinated to surface leads. And then the amines, they'll either be coordinated to over bromines, or they're also, the way that the perovskite structure is by itself, you just consider bulk. It's like, on the faces you have your bromines and your leads, but then in the centers, you basically just need an atom to put outward pressure to keep the cell from collapsing in on itself. So that's what the cesiums are. They're basically putting an outward pressure for the cell.
Mhm.
And since there's an outward pressure, if you have like a finite dot and you didn't have any charge, like say over here, there's going to be a net outward pressure going this way. So you place an amine over the face, and that kind of pushes those plane of atoms to keep them stable. So we can have ligands on there to passivate surface atoms, and it also has like a pressure to keep the whole structure optimized. Or
Pressure or
Which has
probably
stable.
lattice constraint, maybe not really pressure.
yeah, it's more of a strain. I don't know.
I would say lattice constraint if you use additional atoms, which make this really constraint kind of thing on the lattice.
I don't know. Pressure is an intuitive idea to me anyway.
But-
That's why I say pressure. But there's
Yeah,
probably
but
more
when you say
rigorous ways.
pressure, especially when you say like when you
It's not
synthesize,
gas. It's
everyone,
not gas molecules.
everyone
it's-
imagines that you really press your system when you're doing your synthesis,
Mhm.
but this is not what you mean.
Right, it's like an electrostatic pressure force.
Right. So I would say
Hold on.
probably better to use lattice constraint or something like that.
Okay.
So how come that one needs dual type of ligands, anions and
But
cations?
he just explained. He said we have bromines which have negative sign
Okay.
and,
So
and
really,
cadmiums,
yes.
leads which are positive.
So this is common sense argument, but is it the only common sense design for you in your computational modeling, or you based on some literature reading and experimental experience? How this idea was developed?
I've never done it myself, but I'm pretty sure if you just put the oleic acids in, or the carboxylic acids in, if you tried to synthesize it, it probably wouldn't work. So that's one reason why you need both of them. I think another reason is
So
if you
in
just use,
synthesis you need both solutions, so precursors, whatever.
yes, because I think I had it straight earlier. Now I can't remember.
This is- So basically, citation to experiment to support this necessity.
You also have to consider, like if you just put the acids in. I guess they're protonated when they go in, so they don't need charge balancing.
Yeah,
They're
with
in
acids
the
it's
cells.
another thing, are they protonated or deprotonated? What's going on with
So when they
the
go,
Listen,
so it's oleic acid as it
would you like
goes.
to criticize or add some ideas?
Alright, now no.
She may, but maybe she is hesitant. In her research that she was showing,
Mhm.
she does have deprotonated acid,
Mhm.
and then the proton from acid goes to metal on the surface, like cadmium selenium,
Sulfide. But
Huh?
cadmium
cadmium
sulfide.
sulfide.
But this is not happens with carboxylic
No,
acids.
but there is an analogy. So when deprotonated and proton stays on the dot, there is also proton is cation and acid is anion. They kind of also do some sort of movement.
Just a proton.
Yeah. Well, in this case, proton probably would not work, but it is a simplest possible cationic ligand.
Well, in other words, what's happening with your protons? So you start with acid, right? And
Right.
acid means you will have wherever you are oleic or carboxylic
They
acid.
look more like this guy.
Yeah, you will have H, and then this H is dissociating somewhere to the solution probably, right? But kind of what really happening there? How you know that it should be in a deprotonated form?
Because things don't like to exist with charges. So eventually, like, if you have a ligand that pops off, like we took this ligand, pulled him off, and he was just in solution, like this, like,
Then it will be protonated right away, right?
yeah, it's gonna take a proton from somewhere. And it could even take a proton from this amine over here. Because there's gonna be a bunch of those hanging out in the solvent sphere too.
Can I keep asking? So that we will not finish before London comes. Is there any connection to ethylammonium acetate as a chemical compound?
It is a possible configuration that could happen if these two ligands interact in the solvent.
But does ethylammonium acetate exist in nature? Can you purchase it from Sigma Aldrich?
Can you write the chemical formula for your secret?
It is there. It is there. Above his words salvation shell. So when the
I thought that was ethyl ammonium acetate.
yes, ethylammonium acetate. Am I mispronounce it?
I think you said it different. Maybe not. I don't know.
Okay.
But yeah, if you arrange, so if you took this amine and placed it more towards
Uh-huh.
the acid group, it's like they'd be charge stabilized,
Okay.
or
So
they'd be attracted by the charges.
so in some sense you can tell that you passivate your quantum dot with ethylammonium acetate, but while passivating the surface, it dissociates.
That could happen. It's a possibility.
But are you really starting with this compound, or you really start with two different solvents, compounds, whatever?
What is
You mean when doing
experimental?
experiment?
Yes.
Yes,
So
experimental procedure.
they start as charge neutral. So they start in this configuration. There's
As-
oleic acid, and then
As-
oleoamine.
As
Okay.
two compounds,
As
right?
two compounds.
Not as.
Right. They're introduced into the batch separately.
Oh, from
This
different
was-
syringes.
Yes.
This is, and then wherever the reaction happens, they might react with each other, right?
Right.
They might react with the surface through the losing protons or whatever, and passivating with your cation and ion ligands, right?
Mm-hmm. And it would play a role in binding energy because, like, if it's more if the acid, if it likes being bonded to another amine more than it likes being to the surface, like, then that's going to induce it to come off the surface.
And I guess your calculations, if you're not optimizing the structure, probably not really showing the real
Right.
picture which one is more stable.
I haven't
That's
yet.
the-
It's a work in progress.
I would just have a suggestion, because you have really, I mean, like it's a very interesting and important story by itself. What's happening with the ligands on the surface, right?
Mm-hmm.
You probably can really do these calculations and really prepare these things as additional paper, just focusing on the ligands thing
Mhm.
and how they affect the surface, wherever they're binding energy and so on. And here probably just go through just kind of mainly discussing your model based on your experimental kind of analysis or whatever, experimental setup, trying to convince everyone that, oh, here is what we assume is the most reasonable model, and not really focusing on the question which one is more stable or which one is less stable and so on. Because technically you really don't have a good set of data to say to really conclude that this is a more stable structure or not.
Right.
And if since you will be, like, I guess you're still doing this calculation, optimizing, or you can run at any time, if reviewer will ask it, you probably will get more data by that time, right? After because it probably takes about 1 month to get the review answers back,
Mm-hmm.
and then you will have probably more rigorous calculations for really proving that yes, your statement is now proved.
Mm-hmm.
And if no one will care about it, then so like you probably can make a separate paper on role of ligands.
Mm-hmm. Yeah. If it seems
Because
like there's-
otherwise it looks like you have two, like, this question is really complicated and not as easy to proceed, right? Just for understanding the overall idea, how you were doing it and why you're making the statements. So if you're really going in a lot of details just towards this ligand thing, I guess it puts really your focus far from your manganese, whatever, doping contribution.
Mhm. Yeah, if the slide seems awkward, it's because it kind of is, because I made my presentation.
I mean, I would say
had-
you need, like Dimitri's, kind of, if you followed his questions, how exactly or why you're choosing these ligands, why this is a kind of this ratio of these cations, anions, right? If you're just describing your model through some supporting, citing experimental work and just give an overall common sense why you think it has to be this way rather than the other way, I guess this just goes not even to the discussion, but just when you're explaining your model, right?
Right.
And
that's
then
why-
you're not really using these things for any discussion of results for effect of ligands. Because here is a model, right or wrong, but this is what we have, and you have a good reasoning why you were constructing your model this way with these ligands. And then your main question would be focused on the ligand effect, right? Ligand effect, sorry,
Manganese.
doping effect. And then you just go, no doping, here is my electronic structure, the gap is open and ligands contribute or not. You will discuss it probably in your next slide, right? And then when you have a doping, then here is effect, and then the importance of the introducing the spin orbit, the spin polarized, blah, 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 this kind of things, right?
Mhm.
So I would say you probably really move this discussion from discussion to the model building, or how we call constructing the model. You can put it probably, I usually put it in the methodology part, or you can start your discussion with your model explanation or whatever, model introduction.
Mhm.
But not really go in details with binding energies, which one is more stable or less stable.
Okay, so yeah, just highlights. Or the thing I just wanted to highlight for this slide was binding energies are on the order of EVs, so much
Which-
higher than KT. So
Which we again cannot really trust.
Can I interrupt you before you go forward? Well, this first figure is very important, and can I show something here and ask you a comment on this? So if you have stoichiometry of so many cesium, so many lead, so many bromine, so many of each ligand, how to balance the charge to have it nearly zero?
need 4 more equations.
Huh?
Need 4 more equations.
But what are the numbers, and do you believe that you have close the balance of charges of each ion close to zero?
If I do my mental math, 8, 54.
But does it follow your scheme of ligands? I guess you're trying to ask this, right?
Well,
Can you just use this number of ligands which you use on a
in-
opposition?
instead of right now, there is no time for you to make this math on the fly. You can just generally tell that there are anions and cations, both from core of quantum dot and from the ligand shell, and total number of charges, of positive and negative charges, should total to zero or close to zero. And it is one of the principles of how to deposit ligands. Deposit them in such proportions that total charge will be zero, if it is true.
Mm-hmm. That makes sense. I didn't make the model, so I can't really comment on
But
how it was
you
made.
need to
but-
pretend that you made the model.
Well,
Even
you
if you
need,
didn't.
you need to justify that the structure which you're showing, right, is really reasonable.
I can't say it came in a dream.
No.
As a periodic
I mean,
table.
you can say it, but I guess this will be not counted as a justification.
After you publish, and journalists will start hunting and asking why, you can answer this way.
By the way, they will-
I guess I missed the point. So why the ligand is not in 1-to-1 ratio?
This equation?
You can
You
bring
can
it
see-
To balance the charge, I
balance.
guess, right?
or maybe write it on the whiteboard.
Oh, yeah.
We have a white?
You do.
You can show it here on the device. The
It's
other
okay, I
channel.
think whiteboard will work for everyone.
Braden is in online. He is seeing us, but we are not hearing him. Braden.
Braden or Brandon?
No, Braden.
Braden is online?
Yeah. Oh, now I guess he is here.
Then why we cannot hear him?
I don't know. He just texts us. He's,
Oh, he like he can hear us?
yeah.
Nice, okay. Say hi to him.
Well, if you say hi to him out loud, he probably hear it.
Yeah.
So based on stoichiometry, like these are pretty much fixed. So for a 2x2 cell, that's 8. 2 by 1 minus 54. So that's 8. And then, so then basically you just have to do, like, find a good ratio of those two between the ligands to minimize that number.
I see. So the perovskite itself is neutral, right?
Yes.
And your ligand is 1 plus and 1 minus.
Periodic crystal, three-dimensional crystal, is neutral. But
Yeah,
if you cut surfaces, you can get excess of anions or excess of cations.
The idea is that his number of positive lands, negative bromines, right, and positive CS, what is it?
Cesium.
Cesium. They are not really equal to each other because of this reason. When you cut from the surface, you might have surface enhanced by cations or enriched by cations or by anions.
So basically all the bromides or halides that would be popping out of the surface aren't there anymore. And they're replaced by
Like,
ligands.
Alisa probably can comment on it, like when she, well, you were not really making your quantum dots, right? But you remember Levi was making it for you, taking it from a bulk,
Yeah.
sulfide, right?
Yeah.
And you remember like one surface is having just sulfur on the top, another surface having only selenium on the top. And if you have stoichiometric ratio cadmiums and seleniums or sulfur 1 to 1, then yeah, everything is balanced. You have no charge. But if you cut souls that like those which is, if you have a surface with sulfur and then you cut the other surface which also sulfur, possible, right? Then you will have actually extra sulfur on the surface, and it would be charge case, positively charged, or backward if you have surfaces terminated by cadmium, leaving also then on the top and bottom, then you'll have more positive charge rather than negative charge, right? And this charge can be balanced by cation or anion ligands. And in your case, looks like you have not the same, not stoichiometric number, means not exactly the same number of positively charged lead and cesiums versus negatively charged bromines.
Mhm.
That's why he needs this balancing it by ligands.
So, yeah, I think we were tired of the last slide, so I moved on. So here we look at the actual molecular dynamic trajectory for both of these systems. And so for the intrinsic quantum dot, I should mention that both of these, they're computed with either spin restricted or spin polarized calculations. So the intrinsic quantum dot, from looking at the Konchav orbital fluctuation charts, which are shown here, so basically all the little colors represent orbitals, and then their fluctuations is energy time just from the following potential energy surfaces.
Just kind of a comment on the word. I think intrinsic looks a little bit strange because you also have intrinsic properties of your dot case, right? I would suggest maybe instead of intrinsic quantum dot, call it pure or pristine
Mhm.
and doped, like pristine and versus doped, something like this. Probably it makes a little bit better sense than intrinsic. Why you cannot have intrinsic doped quantum dot?
Yeah, I guess.
But
No, I guess it
just on
makes sense.
terminology.
Mhm.
I don't know.
I know. I've been using intrinsic for like 6 months now, so it
I
seems
know,
natural.
but did you get it from some other papers or it was your own word?
I think Dimitri said it once, and then we just kind of stuck with it. So
Again,
it's
if
open
you-
to it can be revised.
If you talked about like semiconductors, right, bulk semiconductor doped versus, usually they call pristine versus doped, or just call semiconductor versus doped semiconductor. Intrinsic, but
Intrinsic, it is in the community of engineers and technology when one speaks about bulk semiconductor.
okay, so
But maybe in colloidal it will be not as.
I would suggest use it pristine. Have it pretty much the same things.
Pristine, and then in brackets. Intrinsic.
But, well, whatever, just a comment. Okay.
So, yeah, so these fluctuation charts, you see that along the trajectory that there are states that kind of go lower than where the orbital started out at, and those are usually indications of trap state. Well, for me, they'd be indications of trap states that occurred during the trajectory. So just to illustrate the point more clearly, I took a time step, which is illustrated around this black box. I took the position file from there and just did a single point calculation. You can see that there's a little hump inside the gap. You can attribute that to surface states.
But did you check it?
I didn't.
If you took already the slice, the snapshot at this specific time, right? You can look on your orbitals and really see where this thing is localized. Is it localized on the ligands?
I mean, I could do that, but then I run into the danger of, well, it's spin restricted, but then the system's really spin orbit, so I feel like I'd be
But
provoking.
here spin.
So this is spin restricted calculation. And then I was going to mention that.
But your spin restricted is needed only when you have your margins. When you have a pristine and a quantum dots, it's probably not so much important, right?
There are people in community who would not agree with this.
So, but your calculation showing if you have spin restricted versus non-spin spin restricted for the pristine quantum dot, you see a big difference?
The band gap, which is so in the conduction band, that's where the band edge is the p orbital, which sees the half energy splitting. So there's potential for it to be covered up by the spin state.
So then your spin restriction is really important even when you don't have d orbitals from margins.
Ideally, one should do everything with spin orbit.
Or because you have lead and
Yes,
bromine,
yes,
that's why.
yes.
Okay.
Especially if it is already possible, if it was shown possible, then it is more correct scientific, less danger to be hit by all the.
But your dynamics is done without spin restricted case, right?
Right. And then the
Oh,
fluctuation.
which dynamics? Molecular dynamics?
Molecular dynamics, this
Or,
is what he's showing.
or
Trajectory.
couplings or electronic
No,
structure.
just this picture which he's showing, adiabatic molecular dynamics, right?
Yeah, we can skate by on that because the forces on the atoms aren't going to change drastically between spin orbit and spin restricted. So your electronic structure is going to be not the same if you did spin orbit, but you'd expect the.
But again, it's not. It costs you nothing really to look on because you already have your dots showing. Take a look on actual distribution of orbitals for this specific state, right, which is inside. It doesn't matter what because of the same reason you said like, oh, we're not expecting that motion of ions will be affected by the spin case, right?
Mm-hmm.
It's only electronic structure which is affected. But it's really, you're thinking it's motion of atoms which cause the state kind of being special, being really inside the gap.
This one.
Because
Yeah, I would expect that.
because it happens at some special moments, right?
Mm-hmm.
Some gap is opening and then it's closing, open and closing at some moment.
I
in
just
time.
chose this point because it's obvious that this.
Right.
would be a trap
So that's why I
figure.
said like nothing wrong and really like again it probably goes to supplemental, it's not your main point, but definitely would be since you call it trap state,
Yeah, just get a
characterize it
global
shows that
picture.
it's localized because maybe it's still spread over the entire system. And if it's spread over, if there is no localization, and for whatever the reason makes this gap going down, who knows, then you cannot call it a trap state.
Did you watch the movie of interatomic distances? Is it because of
Is it when when your
temporary
molecule is disattaching?
popping up?
None of them popped off. But
Okay.
I,
But then it's probably really localization on maybe some side of the quantum dot, or maybe on the ligand.
yeah, I think it's just due to if you consider like the surface is just a bunch of harmonic oscillators of the
Okay.
PB and
Uh-huh.
ligand. If you have enough of them in phase that are a certain distance away, like you'll have less covalent bonding, but they're still ionically. So it's
Anyway, as
some
a-
point in there. I mean, I could do a whole study on this because I
just
did.
look on the localization, delocalization. Like, is it really localized or not?
Well, we could just do oscillator strings, and that would kind of give an idea. Because homo lumo would should
Well,
go away.
it is interesting to see.
I mean,
Oscillator strength is next level, but on the very basic level, correlation between geometry at this time slice and localization, spatial localization of orbitals.
Mm-hmm.
Just do projected, how it calls, projected charge. P
Bar
chart.
charge, yeah, bar charge.
Bar chart, yeah. Files for actually just for this state,
Mm-hmm.
and maybe you can do it for the case when your gap is open and the case when your gap is closed, just two structures.
Mhm.
And you suppose that those where your gap is open, your, whatever it is, it's unoccupied state, right? Your luma would be spread over the quantum dot, right? Or maybe it will be inside the core, I don't know, but it will be spread, will be delocalized. And if you look on this case when your gap is closing, you're expecting that your charge density will be probably sitting maybe on one surface, or maybe just on a ligand. It would have some localization.
Mm-hmm. Yeah, I get what you're saying. So then, I guess we kind of covered the point about average lead oxygen bond length during the trajectory. I have this Excel file to do. I just haven't gone through and processed the data yet. So I think.
But
we should be able
analysis of this bond telling you that it's not really broken, like you always have a covalent bond during the dynamics.
Right, but you should be able to see like a range of distances that it covers in some way. They'd be able to correlate the range to electronic structure. And then, another relevant point is, we did spin orbit oscillator strengths for about like 50 time steps, so you can track the oscillator strength in time along the trajectory. We saw that there was a definite phase, or it definitely oscillates. And I don't know if I had to guess.
So it doesn't fluctuate abruptly, but it fluctuates continuously?
Well, not continuously.
Oscillates continuously?
Well, not totally.
But it's having some
continuously,
phase
but yeah, you can
means-
see that there's some sort of oscillation phase. It's not perfect, but
And
some
what's the period of this oscillation? Does it match any of the
Normal?
normal mode
yeah, that's what I
frequencies?
that's what I was hoping to compare with this data up here.
Okay,
Because it seems obvious that this should be correlated to this bond distance.
But you know what Levi was doing with this kind of things? So, and he has a script, so you can probably just contact him and ask whether he can share the script. He was sharing it with Javed, right? For his analysis of the oscillations in the
I did
bond
not
distance.
I did not take this one yet.
But anyway, you can ask him. But he was just calculating, let's say, he was actually decompose his distances, like all coordinates, like each distance between neighboring atoms, let's say ligands, whatever it is, oxygen and lead, oxygen and, so your oxygen is only connected to lead, nothing to the CS? To the-
Right, all the oxygens are two LEDs.
Okay, anyway, so but you can just look this oscillations, do the Fourier transform. Actually, I think he was doing after correlation function first, and then he was making a Fourier transform from after correlation function.
To get the spectral.
And then yeah, which gives you some kind of frequencies, right? Which would correspond to the normal modes, either acoustic or optical modes, right? Collective motion, which will be really related to this lead or oscillations, right? And also you probably can find in the literature this lead oxygen normal modes for the surfaces or something.
Mhm.
But you can actually do it in between, like you can do it for each pair of atoms.
Right.
Wherever they interacting, or wherever the nearest atoms you have, right? So you can actually do this procedure for wherever your lead brom bonds, right? And see what, in other words, you can kind of get the
Correlation
spectra,
between any.
right?
atoms.
Any nearest neighboring atoms, which give you some idea of the normal modes. Some of them might be really harmonic, some even non-harmonicity will be present through this method, right? Which kind of give you the whole spectra of your vibrations which you have for the system.
Would definitely be handy.
And because you can decompose it on each type of atoms, right, or type of bonds, you will clearly see kind of this connection with going to a question from Dmitry. Does this oscillation, which you already see that you have some oscillation in the electronic levels, does this really relate to the normal ones? Or let's say to this specific frequency correlated with this frequency typical for lead or maybe lead bromine or maybe even cesium lead, even if they're not really creating a bond, right? But they do some kind of motion which might be involved into the vibrational mode.
I think that's how I planned. Well, it's basically the same idea how I plan to process the data. Because in an Excel spreadsheet, you can just choose nearest neighbors by just taking the shortest magnitude. The
But
distance between all of them, and then just
and
looking
again,
at
yeah,
the
you can
changes in the
take
distance
this
period.
and just Fourier transform directly from the bond distance, But I think then you probably will have a lot of noise. And that's why you probably can ask Levi. I think he was doing first you find, but you can do the same, getting the after correlation function between each neighbor, between each nearest neighbor, right? And then do Fourier transform from the after correlation function, which I think he was doing it for the purpose to get rid of a lot of noise and your spectra becoming much more smooth and nice, and with very clear peaks.
I'll have to talk to him when I
Yeah,
see
just
him
an
in
email to
Arizona.
him, ask.
So that's the intrinsic dot, and with the dope system, it's not as interesting. So we did spin polarized. So we have two different energy fluctuations. We have your spin alpha, where those are where all the up spin states are from the manganese, and then these two states here that are kind of separate from everything else are 2D states, or dehybridized or whatever. So they're from the manganese. And you can see that along the trajectory, there's no states that pop up in between them. So surface states don't affect there. And then spin beta, that's where all the valent or unoccupied D states are, where the transitions would come from. They're like the first 5. They're not very spaced out from the perovskite quantum conduction bands, but you can kind of resolve them if you look close enough. And then you don't see any trap states that poke through those either. So along the trajectory, they're unaffected by trap states. And then if you looked at the home or oscillator strength from the spinor orbitals during the trajectory, they're basically constant, but they're just very low, which kind of follows our expectation from the beginning of the dopant being unaffected, or the oscillator strength being unaffected by trap states. And then another possible idea for probably for the future is like the possibility of dynamics of the ligand field along the trajectory, because as mentioned earlier, there's one bond that's a little longer than others, so perhaps at a high enough temperature, it would be convinced to come in and it'll kick another out, so you have some sort of dynamic ligand field going on. But it'd be interesting to look at. I don't know if it actually happens or not. But anyway, so next slide. So now we're going on to non-radiative relaxation of our excited states. So we have a photo excitation, which is an illustrator that comes in, creates an electron and hole pair that behave independently from each other. And
So you excite near the edge of the band gap? Or how far away you excite? Is it hot excitation? Means you're really deep inside the valence and conduction band, or you close to the edge of the valence and conduction? Near the gap.
It's pretty close. I'm used to just seeing orbital levels, so I don't know what the energy difference is.
But you know energy where you excite.
So I know
you
the
should know
state.
your initial conditions, right?
Yeah,
Where-
those are
where
based
exactly
on
you excite.
those are just based on orbital numbers, and I'm not quite sure what the range is off the top of my head.
So like you're not controlling the energy of the excitation? Well,
You can tell roughly. Are you exciting a little bit above the gap or like to the 3 gaps?
Little above the gap, so it's like within an electron volt of the gap, basically.
And what is the gap and what is the like half electron volt above the gap? Which color or which transition energy?
You
Just
probably need-
roughly.
you probably need to show your spectra first.
If-
And it has
yeah,
to be
before
has to
going
be
to
spectra
relaxation, yes.
averaged over room because your dynamics is at room temperature, right? If you take a spectra at some specific snapshots, it's not very representative, right? You need to you can average your spectra over how many steps along trajectory, and then it would be really average over ensemble, because at room temperature it should be really present over all possible configurations, right? So you average your spectra, and then probably looking on your spectra, you can say, oh, I'm exciting at this first optically active peak, which is kind of close to the band gap, whatever it is, in the range of 1 electron volt, or whatever your energy for this excitation, right?
And that's why I basically, my initial conditions are based off oscillator strengths, so that's what I'm familiar with instead of the energy.
But you probably also set
transition.
up the energy, because you're assuming like if you shine light by laser, this is typical conditions for the lab experiments, right? You're usually not using white source of light. You use a laser with some specified wavelengths, and then you're really exciting that specific energy. So, right, and you're probably holding this energy around, not exactly probably wherever it is, 1.5 electron volt.
So do not panic, do not worry. There is no right or wrong frequency. Just be specific. So like we are exciting at
If you show your
purple
absorption,
or whatever.
yeah, if you start with your absorption spectra, as I said, like averaged over how many configurations. If you average over all configurations, I think you just will see very broad. Actually, is it discrete? Do you have confinement effect on the spectra or not? What kind of spectra you expect? With some peaks, or you really having just like from bulk, like this?
It is your chance to go to Blackboard and draw a spectrum.
But maybe he has a spectra.
No.
No, the past ground, that would have been ground state. And I just put bullet points there. So like, if I did spectra, it would have been in part of the slides.
Okay.
But-
Can you just roughly draw it on the Blackboard?
Just schematic.
Something.
Like because it was a kind of surprise for Jabet when he was looking on the spectra of his two-dimensional flakes, or how we call it, not plates.
It's something like,
So you really have nice separated peaks here,
depending on the broadening that we use.
reasonable
it's-
broadening.
But like the
What?
excitations.
But this
Can
is
you
at which
label the
temperature? This is
axis?
already at 0 Kelvin, or when you have
This
the
is
spectrum?
0K.
0
So it's
K.
from geometry optimized
Okay.
structure.
I guess when you do it at room temperature, of course, you will have much bigger broadening for your
I got a separated peak like this one in L point.
at 0 Kelvin.
Yeah, no, at 300
Oh.
and L symmetry.
Oh, because
not in
now
the
we
conduct-
have this
yeah.
L, which is much more distinct from the main.
So how
So it's
can you show
low energy.
how the bulk should look like if you take a spectrum of bulk perovskite? Very roughly, very roughly.
Yeah, probably growing, right?
Okay, okay,
Growing with exponential kind of curve.
okay.
It's
And
not exponential, how we call it?
square.
Square, parabolic. Right?
And the first
Kind of
peak, the
inverse
gap.
of this.
Can you label the approximate energy of the first peak for quantum dot?
For realistic ones or mine?
For yours,
Mine, that's,
Video question?
just put numbers on the x-axis.
Ah,
I think it was like
the energy?
2.4.
I
Okay.
didn't see it. What is it?
2.4 EV, so green.
Okay.
Actually, no, that'd be more.
But this is it's Reese with experimental.
Yeah, just by accident. Because we use PBE for the band gap, so it's about half lower than it should be.
PBE? Functional.
PBE function.
So that underestimates by about half. So the real band gap should be around 3, I think, for the system. Because it's a small dot, so you'd expect it to follow the whatever that quantity
But
So the
the
confinement
size-
effect should be much stronger.
But the size is your quantum dot is much smaller comparing to the what you really synthesize, right?
Right, so it shouldn't be a big blue shift for this one.
And that's why they agree with your
And
2.2.
it just happens to be a
Okay.
0.5 EV plus.
So again, if you're looking on your spectra, it looks like you excited the very first peak or the second peak, which is kind of more intensive.
Second and third. So that's usually, if we're looking at
Well,
relaxation.
that looks like it's deep enough that you really go into the high excited state. Second, I would say kind of intermediate, because your first one probably goes
That's
from
just
the
homonuma.
from the homonuma. Yeah, I think with this one it would be much easier to understand, at least at 0 Kelvin, right? But I would say to be more accurate, to specify your initial conditions, you can take your spectra at room temperature, average over your ensemble, and then hopefully you still will be resolving the 3 peaks, but they will be more broader and maybe shifted a little bit to, I would say they probably will be shifted to red more comparing to your 0 Kelvin calculations. No, because looking on this one, what your orbitals do, they
Oh, I see,
usually
right.
go down in energy rather than up.
I guess, yeah.
So in average, you probably will have smaller gaps than you have at 0 Kelvin.
How do I get back on this slide?
And just very quickly, when you do your calculations, are you including spin orbit or not in this case?
That one,
Or you can do both?
you can do both. That one's spin restricted. Is there another color? But if you do, If you do spin orbit, like this one actually increases a little bit, and then it follows. Well, actually.
Your first big increase in intensity.
Yeah, by about 4 times. Then it follows the same trend after that. So yeah, non-radiative relaxation. So the way that can be modeled is the perovskite is still going to be absorber, so the excitation is going to be on the perovskite, so it's going to relax to the band edges of the perovskite, and then from the perovskite, the electron hole can relax to the dopant states on the inside of the gap, and it's going to happen at some rate, which ideally you'd like them to be at the same rate, because otherwise, like, you'll have a hole waiting for an electron, and where it could be emitting, it wouldn't. So ideally you'd like for the rates to both to reach the manganese states at the same time. So I haven't fully completed these yet, 'cause working out some bugs with the code and the data, but we just start with our intrinsic dot, comparing spin restricted, spin polarized on radiative relaxation. They both relax to the band edges of the quantum dot at about 10 to the 1 picosecond time scales. I guess I'm not sure how that compares to the literature off the top of my head. I can't remember what the reported values are. I'll just look at that. Spinner, non-adiabatic couplings for the intrinsic dot. It's work in progress.
So it's a sub-picosecond range, right?
Yes. I think my initial data showed that they're about on the same time scale, but I don't fully trust it yet. So, and then with the dope dot, that's where the interesting non-radiative relaxation occurs. So if we just do spin polarized calculation, so there's no spin flip, we see
It's much the same, right?
they're actually a little bit different. So they show a little different relaxations, even though the energies of the bands are about the same. I know, it's kind of weird. So for the spin polarized, if we excite a hole deep into the valence band, about 20 states, so that's going to be on the perovskite. And then the population is going to decay. You can see that these little things going up, that means that states are gaining occupation. Then when they decrease, they're losing populations, the states below them. You see that happens pretty fast in the conduction band. And then even once it hits the dopant states, which are close to the band edge, it's like, it takes a little bit of time, but after about 300 time steps, like, all of them relax to the band edge. But for the spinner non-adiabatic couplings, or if you include spin orbit coupling, you see we populate HOMO minus 20, which is in the perovskite band again, ideally. So it decays, you kind of see some quick relaxation from the perovskite bands. They're a little slower. If you're looking closely, you can kind of look at the time steps. But there's not much of a difference here. The big difference is once you get to like HOMO minus 3, HOMO minus 2, there's a big pile up, I guess you could say, a population that occurs at HOMO minus 1, and then it just takes, it's just a very slow.
So it looks like you have some intermediate, say,
Intermediate state.
intermediate state
Right.
comparing to your.
But is it legitimate to compare alpha component and spin orbit? Maybe it reflects the spin flip dynamics, and you need to have both alpha and beta in your spin polarized, and still your spin polarized has no chance for spin flip. So it can be evidence of spin flip transition.
So you're saying like this state where you have this bump corresponds to the spin flip?
Could be. It's not enough data to tell it 100%, but one should suspect it. And spin flip is always slower than all other processes, so that it may happen later.
So you can get spin flips for non-radiative
Yes.
limitations?
Yes. If you are in the basis on spinners, there's
You're allowed to.
you're allowed.
Actually,
Right.
for the non, actually, it's not. It can be not really slow.
Well, it is a
This is
reason
our
why you may
crossing,
want. Yes.
What we call
Why you may want to track the magnetization as function of time.
Mm. Yep.
So if there are no spin flips, then overall magnetization will stay constant. But if you have spin flips, it may just like
Mhm.
change them.
you will have a slab kind of distribution. Spin up, spin down.
I get what you're saying, but I guess from I don't have a good picture in here of it. So basically, HOMO -1 and HOMO of the spin alpha is they're basically same in energy. If you look at the dose as the spinner, so and it's the same energy offset too between the states. So it's not an energy issue. It's
So
an
you
orbital
want to
issue.
say that HOMO and HOMO -1 in spinners have primarily alpha character,
Yes,
so they're not contributed by beta.
right.
That's why it's gonna be a spin flip.
Yeah, that's
So you have
why I didn't consider it anyway. And if you look at the Redfield tensors, like the magnitude of the spinner transitions is about half of the spin polarized, which I'm not really sure why that is, because
Then it would be interesting again to understand the nature of this intermediate luma -1 or whatever HOMO -1 state. Why is it so different from your?
But if you make comparison between spin polarized and spinner, and you're not showing beta component, then you need a very strong argument.
Well,
I
his
guess-
argument because the energy is so.
Oh, it's only for frontier orbitals, for close to home. But when you excite to the HOMO -20, there will be counterpart of the different spin projection.
It could be, but the beta, well, the ones I ran, the betas, they relax in like 10 to the -2 rates. So those happen very quickly.
And it's and it doesn't go. The beta state is not
They don't have
entering the gap,
right.
so it stops much at a different energy.
Mm-hmm.
Well, it is not seen from this figure. If you just add this explanation, it could be fine. But the audience not always consist of mind readers.
Yeah, I guess. Well, I think someone said this was going to be a brief meeting, so I tried to.
Oh, sure. Thank you for making it.
How many slides you still have?
2 more, because we're done with non-radiated now, so we can go to
We
radiated.
will go.
So one slide per 15 minutes. We are kind of on schedule.
So, well, this got edited a little bit. But anyway, so now we're looking at radiative relaxations that can happen in these systems. So, non-radiatively, the holes and the electrons relax to the band edges of the dopant, illustrated here. But you can also have PL that comes intrinsic from the perovskite, because in experiment they do see dual emission from the same samples. But in our systems, our dots are so small that you don't see the same characteristics from just one dot, so we made 2. So you could compare the PL from intrinsic or pristine dot in the dopant. And this notation here, this is just something that's, I guess, conventional in coordination chemistry for describing transitions from these states.
Can you teach us a little bit more about this notation?
So T means triple degeneracy, or yes, triplet for short, and then the upper script describes the multiplicity. So this would be 3 spin-up electrons.
Okay.
And I forget what the subscript is. I think it has something to do with symmetry. But that's not the important thing. So we go from a triplet state to a singly degenerate state that has 5 spin-ups. So basically, this is just a fancy lab code way of saying spin flip transition.
Okay. And what letter A stands for?
Symmetry of the state.
Or A is, it tells you the degeneracy of the state. So it's singly.
This notation should correspond to the symmetry of your state, and it's either A or Angerada, I guess.
That's what the subscript is usually, isn't it? I thought the letters just describe your orbital or the energy states you're looking at.
Well, next time we may just show the photocopy from inorganic textbook.
Or atomic spectroscopy might work as well.
So, yeah, these are best visualized are best described as images rather than words. So if we look just at our pristine or intrinsic dot, spin restricted calculation, so we see we excite right away, and then as it relaxes to the band edges, that's what happens during this time. Down here, you can get possible intraband transitions or luminescence from like LUMO plus 10 to LUMO plus 8 or something. So that's what these describe. And then at about 1 picosecond, electron hole relax to the band edges, and that's when you get your HOMO-LUMO transitions. And then this figure here basically says that the interband transition into these transitions here have higher oscillator strengths, are brighter than the HOMO-LUMO transition for the quantum dot, which is interesting. But so basically it relaxes here for 100 picoseconds, first radiative lifetime, and then we can see the peak here, which is just summing up each emission. And the intensity comes out about 10 to the third units. But when you compare that to the spinner, the interband transitions aren't as bright, and the brightest one is the HOMO-LUMO. And it's not shown on here, but the intensity of this one's up to 10 to the fourth intensity, so it's about 4 times more intense, which kind of corresponds to our spectra because the HOMO-LUMO peak is about 4 times higher, so we give 4 times more intense PL.
I'm just wondering one thing. This intensity unit is atomic unit or just arbitrary unit?
I think when I put it arbitrary, just because I didn't know what else to put. I'm not sure if it's atomic. I think it would just be arbitrary because it's just counting, or it takes an emission from one time step and just keeps adding them. I'm not sure what units they're.
So it's not normalized. It's just integrated emission without specific units.
Mm-hmm.
It's used only to compare relative intensity of peaks.
Yes, and that's why that's one reason we made 2 dots, so we can compare them. And then I didn't do the spin polarized PL yet, just because I don't have an infinite amount of time. I'll get to it eventually. But then the drum roll, the finale that we've been waiting for, PL from the dopant, is very small, about 10 to the 5 times smaller than the intrinsic quantum or pristine quantum dot. And our working theory right now is we're not getting good emission from our DD transition. One is because our simulations kind of cut out at a certain time, so you're not getting the full radiative lifetime. So the peak could be a little bit higher.
But don't you say, I remember for your poster, one of the main results were that you will have this emission from this state only if you include spin orbit.
Yes.
And this is with spin orbit.
This one here is spin orbit, yes.
So it is
But
small but not zero.
If you don't have spin orbit, then it's completely dark.
Right,
And
then
if
it would
you
just
have
be
spin orbit, then you have weak oscillator strength.
So if
And it should be,
yes.
I was going to say, so in experiment, they see that this peak here should be the same order of magnitude as this peak.
But in experiments, they probably don't have a single manganese impurity.
The doping constant, well, for one dot, it's pretty small.
Small, but still probably not a single manganese.
Yeah, that's true. But I mean, well, even
And
if you
then-
had 100
and then
manganese,
again,
though,
Each of them, you will have each of them contributing these D levels. Of course, they might be split due to the interaction between these impurities, right? And this will increase your intensity.
So that could account for maybe 1 order of magnitude. We'd still have another 3 or 4 to account
But you
for.
said it's not, you said it's just 4 times smaller.
4 times?
No, he did
Four
4 orders.
Oh, 4 orders of
So if you look at
magnitude.
the scale, this is 10 to the minus 1, and this is 10 to the 4th, 10 to the 5th
Okay,
scale. So
So
it's
4 orders of magnitude. Yeah, probably then it cannot be the reason for, because you expect that your impurity should be maybe 1% or something like that. Not more than 10% for sure. Maybe not more than 3%.
in experiments I've seen, it's pretty low, but there have been.
But
people just-
low, usually it goes from 1 to 5%.
Mhm.
This is what they call low.
So
So even without doing literal calculation, you kind of know that the DD transition peak will be missed in spin polarized.
Yes,
Because
yeah, one reason I haven't done it is because it's not good.
but for someone
Something like
who looks quick through, it would be very illustrative to show
Mhm.
that it is literally blank on this transition energy. There is
Mhm.
nothing.
And I think you have a better figures in your poster for illustrating this observation. I think in your poster.
Oh, my orbital.
No, not orbital. You were showing your emission spectra kind of with spin orbit and without spin.
Oh, right.
And then it's clearly showing no peak.
Mm-hmm.
The peak.
A couple questions. Your intrinsic spin polarized, time-dependent luminescence, and you have a bracket telling homolumen transition.
Mm-hmm.
Is it possible to make zoom in into vicinity of this transition?
Literally here?
Huh?
Like literally here, or just figure?
No, not right now, but in the future, to zoom in energy from maybe 2.9 to 3.5, and in time from maybe 1 picosecond to 10 picoseconds to show, because right now it is almost invisible for human eye, to show that this feature does exist.
Just make it as like an inset?
Yes, inset, to sound convincing for a reader.
Mm-hmm.
It was not a question, it was a comment. And for same region in the spinner calculation?
This guy? Yeah, like I can't even see it.
For intrinsic.
Oh, true.
Intrinsic and spinner. Yes, here. This orange stripe ends at around 15 picosecond.
Yep.
Is there a way to continue it? Is it on the way
It's,
with maybe frozen propagation?
yeah, it's a work in progress.
Okay.
Because this is artificial, this cutoff here. Like, its radiative lifetime should be longer, but it's just a bug of our code right
Okay.
now.
Okay. And if you do this frozen propagation, if you fix this bug for DD transition, do you expect it to be a little more intense?
It may get up to 0.2.
Okay, better. Will it be bigger than the infrared transition at least?
Yeah, I have
Okay.
been able to just setting my initial conditions as homo lumo. Like, it does get bigger than these intraband transitions, just not much bigger.
Okay.
Now we're back to where we started.
So means we are done.
Well, have I gotten applause yet?
Sure. Questions?
I think we asked them all.
Maybe not everyone. Anyone wants to? Please, Aaron, there's more questions.
I had a question. The EA, that just mean your ethyl acetate?
Yes,
Okay.
or ethyl ammonia.
Okay.
And it's just shorthand I use. I would change it for the paper.
More questions?
Going once.
Question 1, question 2, question 3. Okay, let's upload Aaron once again. So, if you were writing intense and extensive comments, you may submit them back to Aaron so that he will improve presentation.
I saw some notes on there.
So, see you next time at multiple locations, but specifically on Tuesday meeting, right? When everyone will hopefully bring results section for the papers. This will be the hardest part for editing and helping each other.